Hello, this is the second video in the Algorithms 2 series on efficiency and complexity, and it will focus on the efficiency and order of sorting algorithms. To compare the efficiency of two sorting algorithms for a particular example, you could look at the number of comparisons and swaps for each. In earlier videos, in the Algorithms 1 series, we used the bubble sort and the shuttle sort on the list 5, 8, 3, 12, 1, 15, 7 and 6. Here's a table of the comparisons and swaps made. So for the bubble sort, 25 comparisons and 13 swaps, and the shuttle sort, 18 comparisons and 13 swaps. So if we look at the number of comparisons shown, this shows that the shuttle sort was more efficient for this list. To compare how well algorithms perform more generally, we want to determine the order of the algorithm, and this is usually based on a worst-case scenario for an algorithm. Let's keep things simple and look at the number of comparisons needed. Well, what would be the worst case for the bubble sort? When the list starts in reverse order and we need to complete the maximum number of passes with the largest number of swaps to sort it, would be the worst case. Looking at the number of comparisons needed to sort the list 5, 4, 3, 2, 1 into ascending order, we can see that we would need 4 to move the number 5 to the end, or to bubble it to the end, and then 3, 2 and 1, totaling 10 comparisons in all. If we generalise this to a list of size n, then the total number of comparisons would be n-1 plus n-2 plus, and going on down until we got to 2 plus 1. Using the formula for the sum of natural numbers, this becomes n over 2, n-1 in total. As you can see, this will have an n squared term and therefore is a quadratic expression. To determine the order, consider what happens as n gets large, and we can see that it is of order n squared. A similar analysis can be done for shuttle sort and will reveal that it also has quadratic order. In fact, many sorting algorithms have quadratic order as a function of the length of the list. But remember, these are based on worst-case scenarios. Even though they have quadratic order, some algorithms are much more efficient than others at sorting a general list, as we saw with the shuttle sort compared to the bubble sort, with the number of comparisons being reduced. Remember, we don't need to know the full function of the complexity, but just that the highest order is n squared, which will dominate as n gets large. Analysis of complexity is an important part of higher level discrete maths and computer science. For example, a computer takes approximately 0.015 seconds to apply a sorting algorithm to a list of 2,000 numbers. We could then estimate the time it would take to apply the same sorting algorithm to a list of 40,000 numbers. If we are told, we may assume that the algorithm has quadratic complexity. If we work out the linear scale factor between 2,000 and 40,000, we will then need to square it because of that quadratic complexity in order to work out a new runtime. So, the linear scale factor, or in other words 40,000 divided by 2,000, would be 20. We then multiply 0.015 times 20 squared. We would have a runtime of 6 seconds. These rough estimates of runtime will give the computer programmers an idea as to whether the algorithm is feasible in practice or whether they need to go back and rewrite the algorithm or recode. In the next session, 2.3, we will look at the efficiency and order of network algorithms.